So the first question, continue with balance and redox reactions. Last session we talked about balancing an acidic solution. In this question, we want to balance this following redox reaction in a basic solution. So the only thing we're going to do different than what we do in an acidic solution is we're going to add one extra step at the end. So everything else is going to be the same as we did with the acidic solution. Just at the end, we're going to add one additional step. So again, we want to determine what's being oxidized, what's being reduced. So here zinc is a solid. It's 0. In nitrate, we know that oxygen is a -2. So oxygen is a -2, nitrogen is a +5. Of course, on the product side, zinc 2+. And for ammonia, since hydrogen is bound to a non-metal, it's a +1. Therefore, nitrogen is a -3. And so we see that zinc is oxidized from 0 to +2, and nitrogen is reduced from +5 to -3. So we can write these two half reactions. We get this. So there's a total of 8 electrons that nitrogen gains to go from a +5 to a -3. Once we do this, the next thing we need to do is balance the oxygens by adding water molecules. So the first half reaction, the oxidation half reaction, has no oxygen, so it doesn't need water molecules. But the second one, we have 3. So then we need to add 3 water molecules on the product side. So if it has no oxygen, we don't need to add water. Now that we've balanced the oxygen, we need to balance the hydrogen. So again, for the reduction half reaction, we have a total of 9 hydrogen on the product side. So we need to balance this by adding 9 protons on the reactant side. And notice so far, if you check both sides of the equation, the overall charge is 0, because -8 plus -1 plus a +9 equals 0. So now we've balanced the hydrogen, we've balanced the oxygen. Next, we need to balance the electrons. So you see the oxidation half reaction has 2 electrons being lost. The reduction half reaction is gaining 8 electrons. So we need to multiply the oxidation half reaction by 4 so that we get 8 electrons being lost. Now that we have that, the next thing we need to do is add the 2 reactions together. And so when we add the 2 reactions together, the 8 electrons cancel out. And what we have left is this balanced equation. Now, if this was an acidic solution, this would be the point that we stop. However, since this is not an acidic solution, the next step we need to do is add as many hydroxide ions as there are protons. So since there's 9 protons, we have to add 9 hydroxide ions to both sides. So it would look like this. So again, what we did is, since there were 9 protons, we added 9 hydroxide ions to each side. Now these 9 hydroxides and 9 protons can be combined into 9 water molecules. Now you see we have 9 water molecules on the reactant side. We have 3 water molecules on the product side. So these 3 will cancel out 3 from the reactant side, and we're left with 6 water molecules. And so the overall reaction would be this at the bottom. So the coefficient of water is 6, the coefficient of zinc is 4, and the coefficient of hydroxide is 9. Moving on to question 2. So question 2, what we're looking for is to determine which of the following cells would be non-spontaneous. And so You can go through and calculate all the E of cells for all these electrochemical cells and see which ones are positive, which ones are negative. But I was hoping for you to use the standard reduction table and be able to determine it just by looking at the standard reductions of your two species. So for example, in the first electrochemical cell, we have oxygen and we have zinc. And you notice that zinc goes from zinc to zinc 2 plus, oxygen goes from 0 to -1. So what we want to know is which one has the greater reduction potential. If the reduction of oxygen to peroxide is greater than the reduction potential of zinc 2 plus to zinc, then this is a spontaneous reaction. If we find out that the reduction potential of zinc 2 plus to zinc is greater than the reduction potential of O2 to H2O2, then it's non-spontaneous. So we look at the reduction potential table, we see that H2O2 or O2 to H2O2 is right, oh, not that one, is this one, 0.68. And when we see zinc to zinc or zinc 2 plus to zinc, it's negative 0.76. So since the reduction potential of oxygen is greater than zinc 2 plus, oxygen will be reduced. So this is a valid or spontaneous electrochemical cell. So it wouldn't be non-spontaneous. Next we go to the second electrochemical cell. We have manganese 2 plus aluminum gives us aluminum 3 plus gives us aluminum and permanganate. So we see here manganese 2 plus, we get permanganate, aluminum 3 plus to aluminum. Now again, if the reduction potential of aluminum is greater than the reduction potential of permanganate to manganese 2 plus, this would be a spontaneous cell. So again, you look at the reduction potential table, you find out where's the reduction potential of aluminum. It's down here. And the reduction potential of permanganate to manganese 2 plus, it's up here. But wrong one, sorry. It's this one. So you notice that the reduction potential of permanganate to manganese 2 plus is greater than the reduction potential of aluminum 3 plus to aluminum. So B would be a non-spontaneous reaction. It would prefer to go the other direction. Because again, the reduction potential of aluminum 3 plus is less than the reduction potential of permanganate. We go to the third one. We have fluorine plus sodium gives us sodium ions and fluoride ions. Again, fluorine is reduced. Sodium is oxidized. So what we want to know is the reduction potential of fluorine greater than that of sodium. So sodium is down here, is negative 2.71. Fluorine is a positive 2.87. So since the reduction potential of fluorine, F2, is greater than the reduction potential of sodium plus, this reaction will be spontaneous because the stronger oxidizing agent is on the left side. So this would be a spontaneous reaction. Next we have silver reacts with iron 2 plus to form silver plus and iron. So again, we look at our two half reactions. We have silver, silver plus, iron 2 plus to iron. So iron 2 plus is reduced. So the reduction potential of iron 2 plus is greater than the reduction potential of silver plus to silver, then this reaction will be spontaneous. So iron 2 plus to iron is a negative 0.44. Silver plus to silver is a positive 0.77. So this tells us that, oh, wrong one, it's positive 0.80. So since the reduction potential of Ag plus is greater than the reduction potential of Fe2 plus, this would indicate that this is a non-spontaneous reaction. So what does that mean? It prefers to go the other way. It prefers silver plus to be reduced and iron to be oxidized because silver plus has the greater reduction potential. Next we have chloride plus Fe3 plus gives us Cl2 and Fe2 plus. So again we have chloride is oxidized to Cl2 and Fe3 plus is reduced to Fe2 plus. So again, what we're looking at to know if this is spontaneous is the reduction potential of Fe3 plus to Fe2 plus greater than the reduction potential of Cl2 to Cl minus. And so Fe2 plus Fe3 plus is located right here. It's 0.77. Cl2 to Cl minus is 1.36. So again, since the reduction potential of Cl2 is greater than the reduction potential of Fe3 plus, this would be a non-spontaneous reaction, which means it prefers to go in the reverse direction. So Cl2 wants to be reduced, iron 2 plus wants to be oxidized. Lastly, we have nickel plus I2 gives us nickel 2 plus and iodide. So again, you see nickel is oxidized, I2 is reduced. So if the reduction potential of nickel 2 plus is greater than that of I2, this would be a non-spontaneous reaction. So we find here I2's reduction potential 0.54. We see nickel 2 plus negative 0.28. So since the reduction potential of I2 is greater than that of nickel 2 plus, this would be a spontaneous reaction. Nickel wants to be oxidized, I2 wants to be reduced. So here we're given a list of reduction potentials, and we want to write the formula of the strongest oxidizing agent. So for strongest oxidizing agent, that means the species that is most likely or has the greatest ability to be reduced. So strongest oxidizing agent greatest reduction potential. So the one with the greatest reduction potential is going to be the strongest oxidizing agent. And again, oxidizing agents are going to be reactants in the half reactions. Now, strongest reducing agent would be the one with the smaller or smallest reduction potential. And for reducing agents, these are going to be products in the half reactions. So on the reactant side, we have oxidizing agents on the reduction half reactions, and on the product side, we have reducing agents. So A, which one is the strongest oxidizing agent? You find the one with the greatest reduction potential, in this case 1.09. So the strongest oxidizing agent in this set is Br2. Now for the strongest reducing agent, we're looking for the one with the smallest reduction potential, and that's going to be negative 0.4. But remember, reducing agents are going to be the products of the half reactions. So the reducing agent, the strongest reducing agent would be cadmium. So cadmium is the strongest reducing agent. Again, oxidizing agents are going to be the reactants in the reduction half reactions. Reducing agents are going to be products in the reduction half reaction. Now we want to do some calculations involving electrochemical cells. So here we have these two half reactions given to us with their reduction potentials. And we want to calculate the delta G in kilojoules and the equilibrium constant for this following redox reaction. So what you notice here in this redox reaction is we go from Br minus to Br2, and we go from F2 to F minus. So in this redox reaction, bromine is being oxidized, fluorine is being reduced. So when we're given E of cell, or we want to calculate the K for an electrochemical cell, we use E of cell equals 0.0592 divided by N times the log of K. Now the reason we can use this shorthand version of E of cell and K is because we're doing this at room temperature. Because the temperature wasn't stated, it's understood that it's going to be room temperature. If it's not room temperature, you have to use a more elaborate form of this equation. So again, the E of cell is the standard cell reduction of your electrochemical cell. N is the moles of electrons that are transferred. And of course, K is the equilibrium constant. So now remember, bromine is being oxidized, fluorine is being reduced. So to get the E of oxidation of bromide, we change the sign. So the E of cell is the E of reduction of F2 plus the E of oxidation of Br minus, which is the negative of the E of reduction. So we get an E of cell of 1.78 volts. Now the moles of electrons transferred would be in the balanced chemical equation, and we see that the moles of electron transferred is 2. And again, that's always going to be from the balanced redox reaction. So now we set this up, we can solve for K. Since the E of cell is positive, our K should be an exponent greater than 1. So when we find this, we see that K is about 1.4 times 10 to the 60th. Now to calculate delta G, we use this relationship between the cell potential and delta G equals negative NF E of cell. Now again, N is the moles of electrons transferred. F is a constant, the Faraday's constant. And so when we plug that in, we can calculate delta G. So again, since E of cell is positive, it's spontaneous, so delta G should be negative. And again, Faraday constant is 96,500. Now this puts the answer in joules, and then you would convert it to kilojoules. So it'd be about negative 344 kilojoules. So again, when you use this equation, it puts it in joules, and then you convert joules to kilojoules. All right. So the last question wants to calculate the voltage produced from this electrochemical cell. And so again, you had a cell potential table. The aluminum to aluminum, or the aluminum 3 plus cell potential reduction potential was given. However, the cobalt to cobalt 2 plus, or cobalt 2 plus to cobalt wasn't given, so you'd have to look it up on another reduction table. But these are the reduction potentials for these two species. Now what we want to do is, if we first write a chemical equation, we can see what are the reactants and what are the products. So when we write this out, we get aluminum plus cobalt 2 plus yields aluminum 3 plus cobalt. So you see aluminum and cobalt 2 plus are reactants, aluminum 3 plus and cobalt are products. So when we're calculating the cell potential at non-standard conditions, we have to use the Nernst equation. Now, since we're doing this at room temperature because no temperature was stated, we can use this shortened form of the Nernst equation. So again, E cell standard is the standard cell potential. N is the moles of electrons transferred in the balanced equation. And Q is the quotient based on the concentrations of reactants and products. So we know that aluminum is being oxidized because in this shorthand cell notation, what's on the left is what we refer to as the anode side, and the right is the cathode. So the anode is where oxidation occurs, the cathode is where reduction occurs. So we know that aluminum is being oxidized, cobalt 2+ is being reduced. So therefore, to balance this equation, we need to balance the moles of electrons. So to balance the equation, we got to multiply the oxidation half reaction by 2 to get 6 electrons, and we multiply the reduction half reaction by 3 to get 6 electrons. So the electrons have to be balanced before you put it into the Nernst equation. And so from this, we get the Q expression. So notice the aluminum concentration is squared, cobalt concentration is cubed. So we plug in the values of our concentrations of reactants and products, and we get a Q of 500. So this tells us there's lots of product, very little reactant. So as we can imagine, this is going to decrease the cell potential. We know that the moles of electrons transferred is 6 in the balanced redox reaction. Calculate the standard cell potential. Again, cobalt 2+ is being reduced, so it's a negative 0.28 reduction potential. Aluminum is being oxidized, so we got to change the sign of its reduction potential to find the oxidation potential, and we get a standard cell potential of 1.38. Plug it into the Nernst equation, and we get a cell voltage of 1.35, which makes sense because since we have lots of product, very little reactant, the Q is very large, so therefore the cell potential is going to decrease.